Good day everyone! So for this video, we will be solving some problems regarding electrochemistry as part of problem set 1.1. Now the first of these problems requires solving a redox reaction wherein we would be balancing a redox reaction in an acidic medium. Now this problem was taken from Analytical Chemistry 7th edition by Christian Dasgupta and Shu. It reads balance the following reaction. FeS plus NO3 minus goes to form Fe3 plus NO2 plus S. Now the general procedure that we will be doing for balancing redox reactions is that we will be separating them into the oxidation half reaction and the reduction half reaction. So the oxidation half reaction is FeS goes to form Fe3 plus S plus 3E. Now why is this the oxidation half reaction? Because from a 0 charge, the iron goes to a 3 plus charge, so that indicates a loss of 3 electrons. This is why it is the oxidation half reaction. Now the reduction half reaction is the NO3, wherein NO3 minus gains 1 electron to form NO2. But this is not yet balanced, so to compensate for this, we will be adding water molecules. So balancing the reduction half reaction, we added a water molecule on the right side here to balance the number of oxygen molecules, and to counterbalance the addition of water, we will be adding two hydrogen ions, 2H plus ions. Now, since the oxidation reaction involves 3 electrons, there is a need to multiply the reduction half reaction by 3 so that the number of electrons would cancel. So we will do this for the reduction half reaction, which gives us this reaction. And now we will combine the two half reactions, canceling out those reactions, those elements, which we see on either side of the equation, which is the 3e. So we will cancel that, and that gives us a final balanced reaction, which is this reaction here. That's 3H2O. Next on our list of reactions is balancing a redox reaction in a basic medium. Now this problem was lifted from Chemistry 12th edition by Chang and Goldsby. Balance the following reaction. BiOH3 plus SnO2 2 minus goes to form SnO3 2 minus plus Bi. Again, the way that we will be tackling this is we will separate them into the two half reactions, oxidation and reduction. So the oxidation half reaction is the SnO2 one. Why is it the oxidation half reaction? Because the oxidation number for tin here is at a 2 plus, while the oxidation number for tin here is at a 4 plus. Since the oxidation number for tin increased from 2 plus to 4 plus, there is a loss of 2 electrons here. So that is why this is the oxidation half reaction. And again, we will be balancing it by adding water atoms. And since this is a basic medium, instead of counterbalancing the addition of H with H+, we will be counterbalancing that with OH, as seen here. Again, for the reduction half reaction, this is the reduction half reaction because from a 3 plus, from an oxidation number of 3 plus, remember that OH is negative 1. Negative 1 times 3 is negative 3. So for this to have a neutral charge, Bi should be, this one should be on a 3 plus. So it involves the the gain of 3 electrons. That's why we have here only bismuth. And again, we will be adding OH to counterbalance the reduction half reaction. And so we have here. Now we have here our two half reactions. Notice that for the oxidation half reaction, we have 2 electrons, while for the reduction half reaction, we have 3 electrons. There is an imbalance on the electrons. So what we will do is we will be multiplying this oxidation half reaction by 3 and the reduction half reaction by 2, such that we may cancel the number of electrons. So balancing to cancel the electrons, again, we will be multiplying 3 to the oxidation reaction and 2 to the reduction reaction. And then we will be combining the two half reactions. And again, we will be canceling the terms that appear on both sides. And in this case, it's the 6 OHs and the 6 electrons, which gives us a final answer of this 2BiOH3 plus 3SNO2 2 minus goes to form 3SNO3 2 minus plus 2Bi plus 3H2O. Now for a problem with regards to an application of Coulomb's and Faraday's laws, this was taken from Fundamentals of Analytical Chemistry 9th edition by Skoog and West. It reads, a 0.1330 gram sample of a purified organic acid was neutralized by the hydroxide ion produced in 5 minutes and 24 seconds by a constant current of 300 milliamperes. Calculate the equivalent mass of a acid in grams. So we must note of this, since the problem states that the reaction involves the hydroxide ion, we would assume that we only have 1 electron that participated. So this is in a 1-to-1 basis. Why did we assume this? Because we do not have the specific organic acid, and since it only calls for the hydroxide ion, so we can assume that it's on a 1-to-1 basis. So we will be listing the given. We have our mass, our time, and our charge. Our mass, which is 0.1230 grams of the sample. Our time is 5 minutes and 24 seconds. And our charge, which is the current, is 300 milliamperes or 0.3 amperes. The required is the equivalent mass of the acid in grams. So for the solution, we will first compute for the charge via this formula. Q is equal to IT, where I is the current and T is the time. So we will be multiplying 0.300 with the time. We will be converting the 5 minutes into seconds for dimensional homogeneity, and since our intended unit is in coulombs and coulombs is in ampere seconds, so we would have a consistent answer. So multiplying that will give us a charge of 97.2 coulombs. And then we will substitute that to this formula for the equivalent number of moles, which is the charge over the number of moles of electrons multiplied by Faraday's constant. We have here, and we multiply that by 1 equivalent of the organic acid. We have the number of equivalent moles of the organic acid to be 1.00741 times 10 to the negative 3. But this is not yet the final answer, as this is still in moles. We would want it to be in grams. So to do that, we will be dividing our sample mass with the number of moles for the equivalent of the organic acid. So that's 0.1330 grams of the sample divided by 1.00741 times 10 to the negative 3 of the equivalent organic acid, and that gives us 132.022 grams of our organic acid. And this is the final answer. And lastly is an application of the Nernst equation. Again, this problem was taken from Fundamentals of Analytical Chemistry 9th edition by Skoog and West. Now calculate the potential of a platinum electrode immersed in a solution that is 0.0160 molar in K2PtCl4 and 0.2450 molar in KCl. Again, we will be first listing the given, which is our concentrations, and the required is the potential of the platinum electrode. So for our solution, we will be looking at the standard reduction tables to certify, to look at what type of reaction happens, and the reaction in the platinum electrode is given by this electron here, which is PtCl4 2 minus plus 2 electrons goes to form solid platinum metal and 4 chloride ions. Why is this the reaction? Because it corresponds to the given concentrations, which is K2PtCl4 and HCl. Now the standard electrode potential for this reaction is plus 0.755 volts. Now we will then plug the molarities into the Nernst equation. Now this is the form of the Nernst equation that we will be using. Notice that in the problem, it was not stated what the temperature of the system is. If the temperature of the system is not given, it may be assumed that the reaction happens at room temperature, which is 25 degrees Celsius or 298.15 Kelvin. If this is the case, then we may also use the log form of the Nernst equation. However, I just opted to use the natural logarithm form of the equation. And we will be substituting this into the Nernst equation. This is our standard electrode potential, the universal gas constant, temperature in kelvins, the number of moles of electrons that participated. Remember that there are 2 electrons that participated in the reaction, Faraday's constant, and the natural logarithm of the reaction quotient, which is the concentration of the products over the concentration of the reactants raised to their stoichiometric ratios. Remember that for the Cl anion, there are 4 of them. That is why this 0.2450 molar is raised to 4. Now computing gives us this equation, which is 0.755 minus negative 0.01915, and plugging that in, our final answer is plus 0.7742 volts. That is the potential of the platinum ion. That is it for this video. Thank you and have a nice day.